So here we have a hypothetical data set. This hypothetical is hypothetical because we have conjured, created it from our head, where you have the number of DMUs, decision-making units, that are 6 in number. We are assuming that they are only using one input, which is staff, to produce one output, which is sales. This is just for simplicity. As an example, DMU1 is using only one staff to produce one sales. DMU3 is using 4 staff to produce 2 sales. So in reality, it's like when you look at DMU4 and DMU1, DMU4 is not doing too good, because if DMU1 is using one staff to get to 1 sales, then DMU3 should have been using 2 staff to get 2 sales, but it's rather using 4 to get 2 sales. So this data set, if we want to know which DMUs are doing well, let me show you what ratio old analysis will do. Okay, old, this is the old star. How do you measure the efficiency of each firm, each DMUs? Well, simple ratios will say that if you divide the sales over the staff, you'll be able to know how much each is doing. So you take each sales divided by staff, each sales, this is a simple ratio analysis. That's what they do in return on asset, return on equity, expense to premium, financial accounting ratios. That's what they do. And when you look at that, you will notice that which firm is doing well. You can tell me. Using ratio analysis. DMU what? DMU2.
DMU2.
So DMU2 is doing well. Okay. DMU2 is doing well simply because it has the highest value of 1.5. This is ratio. It has the highest value of 1.5. While this is good analysis, but there's a problem. Okay, one of the problems is that this analysis is partial. First of all, why is it partial? It's partial because there are only one input and one output, but life is not one input and one output. Life is multiple input, multiple output. Smith, and these papers, I want you to please go and download them and use them. Okay. Smith, 1990 paper, explains this in simple language. Second, it assumed constant returns to scale. So if I should increase the inputs by 10%, the output are going to rise by 10%. If you like do that, you see that's the case. But that is not how the real markets work. Because in the real market, you can increase the input by 10%, the output will rise by more than 10%. You can bring one player alone, and the number of scores in a particular Premier League team will go up significantly just because of that one player. Or you can bring one player to the team, and then the percentage of the score at the foot winnings will go down very significantly. So in real life, things are not constant as it is. It's not like 20% leads to 20%. Also, you cannot identify benchmarks. You can't identify who the role models of the bad ones are doing. For example, if you look at these trends and you see that those that are not like DMU2, they are not doing well, they are below, who should they go and copy? Ratio cannot tell us anything. Anything. And then if you get a score of 1.5, what is driving that score? That 1.5, what is really driving the score? Can we split it and know what is the contribution? Who is contributing to the 1.5? What is the contribution of staff relative to sales? I mean, you don't get it. Is it the staff that is driving that 1.5 or is it sales that is driving? Which one? You cannot find the sources of that performance ratio. That is not to say that accounting ratios are bad, okay, so bad that they can, no. They are simple, you can calculate them, understand them, okay, And when you read all of those papers, and my advice is to read all of those references, you can look at one aspect of the firm, for example, a corner of the firm. Okay. But like we have already said, you don't deal with multiple inputs and outputs. So what do? Let's go and use regression. A lot of econometricians and operation scientists have used some of these approaches all of the time, altering approaches to be able to now get to better ways. If you use regression, what regression would do is I would throw a line. It would throw a line in between. The regression will find the mean, the line of best fit. And then it will find out how far each one is from the line of best fit. In this case, the green line. Okay, DMU1 is closer to the line, DMU2 is far away. Now, those firms that are far away from the firms, the error is said to be positive. Those that are below the line, the error, which is the error term, the residual, is said to be negative. Now, what the regression line does is that it will minimize the error sum of squares using the principle of ordinary least squares. It will minimize the error sum of squares, okay? And then after minimizing the error sum of squares subject to the necessary constraint, it will now find the beta parameters, which is the coefficient. And the coefficient will tell you by how much the estimate of staff is affecting the sales. Okay, so you can do a regression line. In fact, most of you in your own can quickly do the regression line right now. So what I'm going to do is that I'm going to just show how one of you can do that. So let's just pick one of you. Okay, let me just showcase this one. So when you look at this carefully, you will notice that the regression line, the R square is 73% approximately, which shows that the independent variable staff is explaining 73% of the variability in the sales. That is what it means. But you can now see that the coefficient of the X, which is the staff, is 69%. Okay, so what it means is that a 1 unit increase in the staff will increase sales by 0.69 units. So you are able to know by how much sales is affecting that. By how much staff is affecting sales. So regression is able to tell us something here by how much. But what if there are, again, multiple inputs? What if there are multiple inputs like staff, capital, labor, deposit, all of that? Okay. When there are several other things, there is a bit of a challenge for the regression to do the work now. And besides, this is for the entire industry now. So how do you now pick on individual firms and how they are actually functioning? How the individual firms are actually working relative to their colleagues. While this is possible, though, through a stochastic frontier analysis, there are challenges as well. And what are the challenges? Now follow me here. So let's begin to look at the challenges. The first thing is that the distance to the line is a relative measure. Now, the thing about the regression that you saw is that overperformance is said to be when you are above the line. So it means that DMU2 is performing too much. DMU4 is performing too much. Okay? And underperformance is when you are below the regression line. Now, the stochastic frontier analysis, what it's doing is that it will split, you see, the error term is the distance between the line and then the observation. And that is the error term, as we know it in the normal regression. But the stochastic frontier will say that part of it is the error and part of it is the inefficiency. The inefficiency. And the stochastic frontier is based on the mean. The mean. But the mean is the average. But would you want to compare yourself with the average or you want to compare yourself with the best? Secondly, the relationship between the input and the output is said to be linear. That's why you have a linear regression line. But life is not always linear. Life can be nonlinear. Life can be piecewise linear. Okay, and so whilst that one is great, there may be other issues. We use one input, one output. In a dependent, you have the dependent variable and independent variable in a regression. The dependent variable is one, which means is the output. But then, what if there are multiple outputs? In fact, there's something we call stochastic distance function. And even though that can handle multiple inputs and outputs, there are challenges as well. And all of these have been discussed by Lampard and Helgers and all of those papers to see that. The other thing about stochastic frontier analysis, which is sometimes slightly worrying, is that you have to specify a regression model. And in specifying the regression model, you have to specify the distribution of the error time. The distribution of the error time, is it normally distributed? Is it half normal? Is it truncated normal? Is it gamma? Is it Weibull? Is it what kind of distribution? And sometimes you have to do all kinds of specification, and then you run into a problem of specification test. Inefficiencies, not just the noise, or even the inefficiencies, you have to specify the distribution of the inefficiency time. And then as you go through the regression, you have to check whether assumptions have been met. Remember the assumptions of the classical linear regression model. Oh, dear me. Linearity, normality, heteroscedasticity or homoscedasticity, okay, autocorrelation, different levels of autocorrelation if it is a panel data, specification errors. All of these things are a bit complex, restrictive. And then we are not able to get some of the axiomatic properties of production economics. We are not able to clearly determine convexity, that is economics, concavity, free disposability or monotonicity. We are not able to get these things. Each one of these terminologies, you just have to learn them on your own. So what do? Because of this, we now resort to the third way of measuring efficiency and dynamic productivity. And now, ladies and gentlemen, the third way is known as data envelopment analysis. Data envelopment analysis. He was a heavyweight, practically he was a boxer. Okay, and then he became a heavyweight in the field of economics. It was propounded by Chance, Cooper, and Rhodes. Professor Cooper, is well known to have been spearheading this a lot. Eduardo Lao Rhodes was their PhD student. And Cooper and Chance, who supervised Eduardo, actually teamed up and wrote a paper which was initially submitted to the American Economic Review. It was rejected. And finally, it was published eventually in the European Journal. Sorry, it was submitted to Management Science, which was at the time the top paper in the world of operations and management science. When it was rejected, it was sent to the European Journal of Operations Research, and now it was accepted. And now it has been so much referenced to the extent that I guess management science would wish it was rather sent there. Data envelopment analysis. What is that? The word data means that you can't do this without data. Take note. You cannot do this without data. The word envelopment comes from the word envelope. Envelope. Envelope is like covering, cover. De-envelope is to remove the cover. Envelope is to cover. So the way you look at an envelope, when you open the envelope is like rising and bending. It is not like a regression, so it's not parametric. It is non-parametric. It is a frontier method. Why? First of all, it's a method, just like ANOVA is a method, just like regression is a method, just like Six Sigma is a method, just like structural equations modeling is a method. But this is a frontier method because the focus is focusing on the frontier, the boundary of the production possibility set. It is the boundary of the production possibility set that we call a frontier. I'm explaining these key terminologies for you to be able to understand so that you can now understand the basic of DEA. It was developed by Chance, Cooper, and Rose in 1978. Later on, you will learn that Banker, Chance, and Cooper, by then Eduardo Rose is gone. Banker, Chance, and Cooper extended it to cover variable return scale. So it is this CCR. They developed the constant return scale, these guys. And then the BCC developed the variable return scale. So sometimes you see their names being used to represent the returns to scale that they extended. What is DEA? We said it's non-parametric mathematical programming methodology, not econometric. So we don't technically have parameters, estimates. It's non-parametric. Just like you have coefficient in regression and stochastic frontier. Yeah, you don't have that. You have non-parametric tools. What is it? It's a linear programming frontier optimization method. Linear means that you are dealing with lines. But of course, in regression, you're also dealing with lines. So, well, here it is linear programming. So it's not just one line, it's multiple lines, pieces. And the goal is to optimize, which means you minimize or maximize. What does it do? It assesses, it calculates, it measures, it evaluates the relative efficiency. Why relative? Relative because by the time you determine the efficiency of one DMU, it is in relation to that of another. So for example, you don't say that this man is short. The moment you say the man is short, you're comparing the man's height with what? Another man. So the measurement of his height is relative. Efficiency is relative. So when you say that this guy is inefficient, you are comparing that guy's efficiency score with another guy. That is why you are saying is inefficient. So the efficiency is relative. So you are measuring the efficiency of homogeneous DMUs. As for homogeneous today, you understand. Because we said homogeneous means that they are using similar input to generate similar output. They are doing similar things. So how does the DEA now come out with a score? Which score? Whether it's a technical efficiency score, allocative efficiency score, cost efficiency score, profit efficiency score, any of the scores, first it has to construct a function, a frontier, a production frontier. Okay, now let me show you something when it's constructing the production frontier. The production frontier construction, it is something like this, okay, like a production function. If it is a cost frontier, it's like an isoquant. And if it is a profit frontier, it is also like a production function. Or sometimes it's like, you know, output possibility set. So what it does is to construct this frontier first. How does it do that? How does it do the construction of the frontier? Well, it does that by using the observed unit. So when the DEA data is scattered, it constructs the frontier. We're going to look at that. And it uses from the unit, it will identify the best practice firms, the top guys, the superpowers, the super champions. It will identify them. These are called best practice firms. And it will use a certain principle, which according to Tanasoli's book, the minimum extrapolation principle. And that principle is simply the convexity assumption and then the free disposability assumption. These two, minimum two. It It will use those two assumptions, and it will now determine the score of the firm, both those that will become efficient and those that will become inefficient. How does it detect the efficiency? Follow me here. So when you are going to explain DEA in most of your work, these are some of the things you'll be saying using the references here and the recent references you know. So I'm going to be ending here. The relative technical efficiency, this is how it estimates it. It does it using the distance of, okay, the distance between the frontier you constructed and every firm on the frontier or inside the frontier. I want to repeat that. It uses the distance between where the firm is located in the production technology set and the constructed frontier. So how far are you? How far is everybody from the frontier is created? And those firms that are on the frontier, then it means that your distance between you and the frontier is zero because you're already on the frontier. Those firms are called efficient. And those non-frontier firms are called inefficient. Non-frontier means they are not on the frontier. So once those firms that are on the frontier have been identified, it will now determine the sources of the inefficiency for those firms that are not on the frontier, the inefficient firms. We call them dominated. It will determine their inefficiency. Because you don't just tell me my score, tell me how inefficient am I. Then it will rank all the firms. It will identify those that should improve and where they should go to, their target that will show their improvement. It will now be able to use that to advise management that, look, this bank is not good. Why is it not good? Because it's producing this input and this output. Okay, good. So why should it be good? It should be good because of this and this. Okay, what should it do to be good? Well, it has to reduce this input by 28%, that input by 28%, increase that output by 30%, and then it will be reaching this target of that, and then it will be efficient. You are giving policies, managerial policies. And so DEA is said to be a benchmarking methodology. Benchmarking methodology. Now, next time, what I'm going to do is I'm going to use the data you have created, and I'm going to use this data now to make up how the DEA does the work. Oh, let me see, I can just do that very quickly. Okay. So this is a scatter plot data that you did. All the firms have been allocated. And please note, I did this by hand. So when you're doing your sample example, you will also do them by hand. Every firm is scattered. What DEA does is that it will construct a frontier along the firms on the northeastern part. So when you look at the production possibility set, this whole gray area is a production possibility set. Okay. And this is a true technology set that you see here. Okay. Now, so it will construct a frontier like this. And then those firms on the extreme left in this context, remember this is input and output. Okay, it will pick them, the first one, it will draw a line from the first one to the next one, and the extreme, on the extreme, to the extent that by the time those piecewise lines have been drawn, there is no DMU on the frontier. There's no DMU on the left of the lines of the constructed green frontier. So how does it do that? This is it. Watch. The DEA will construct a piecewise linear convex envelopment. It's a very long word, but don't worry, because we know what piecewise is. Piecewise is small piece. Linear means that once I was drawing the piece line, I was making them straight lines. I was not making them, curved lines. No. It's an envelopment because, as you can see, if you pick the green, it's like you are now covering it onto the others, like an envelope covers a paper. And it is convex. It's convex because you can see that it is kind of bowed in. It's bowed in. It's not bowed out. It's bowed. It's like they are bending their head down, sort of. The line is bending its head. So what it does is that it will construct this of all the data points. It will then identify a subset of the firms that are efficient here. We call them best practice DMUs. They are the ones who are used to construct the boundary, the efficient boundary. The boundary here means the edge. And they will now envelop all others, including themselves. That is, if they are part of it. Then the efficiency of every firm is assessed. Every firm, including those on the frontier, every firm's DMU efficiency is assessed in relation to the frontier that has been constructed along the input direction. If it's an input orientation or output orientation. Whenever you are doing your work, you have to select which orientation you are to use. If you are to use input orientation, you ask yourself and find out. If you are to use output, you check. If you are to use both, you check. So this has to be discussed with your supervisors. So next time will come, we are going to explain which firms are efficient and which firms are inefficient, looking at this constructed frontier. And of course, looking at the DMUs in the